Thank you so much. And well, this is the last day of this intensive course on continual learning. Yesterday, we had a brief introduction into several methods, well, in general, into taxonomy of methods solving continual learning. We talked a bit about the baselines, and we dived into regularization and architectural methods. And today, we will focus on the two final groups, which are replay and generative rehearsal methods. So these were the part of the methods that use some form of a memory, in a sense. And then we will talk a little bit about the future of continual learning and maybe some more discussion on side topics, events, and so on. All right, so as we talked yesterday, the easiest way to solve forgetting is full replay, where we keep on adding the data samples to our data set and then retraining the entire thing from scratch. It's based on the frequency of updates and so on, we can define how good it is. Although, as you remember, we looked at the results of this retraining and saw that it's actually quite important to get as much data upfront to the model as possible. Otherwise, it can land in some local minimum, and then it's not gonna get out of it. So the good news about the methods that we will talk and discuss today, the replay methods, those that are, well, you actually mentioned yesterday as one of possible solutions, so replaying the data from the past, is that this is very general and effective. The bad news, or maybe like the important features of the replay, so replaying the information or the samples from the past, is that it approximates the IID distribution, so it's not fully IID. It's often seen as cheating when you actually look at the comparisons between methods. So when you replay the data from the past, some of the orthodox continual learning folks would tell you that you shouldn't have access to any data from the past. You should just stick to the model. And obviously there are the limitations in terms of memory and complexity or computational cost of replaying data from the past. If you have a fixed amount of memory, you always have to choose between storing the samples or perhaps storing some more complex model parameters. So, is forgetting solved with replay? So in other words, if we are able to replay the data from the past, are we okay? Are we, do we need any other fancy methods, or are we just fine? Just let's assume that we have, all the access to the past data without limits on the buffers. Does it solve forgetting? What's your intuition? Based on yesterday's discussion, it's going to be an easy question, and since it's a yes or no question, then you have 50% chance of guessing the right one. So.
If there exists a model that can solve a problem that is not continual, then we can emulate the model basically by training on the full data set.
So is it yes or no?
It's yes. Still we can emulate the whole model that will be trained without continuity of the training. We just take all the data that there is and don't do anything until we've got everything, and then train the model. If a model can be trained in that way, then yes, it is still. Okay,
let's maybe look at the results before maybe digging more into your answer. So this would be like the setup where you have a cumulative data set. So you accumulate your data set, you add more and more samples, and these are the results that you're getting when you're replaying the samples from the past. So as you see the baseline, so the the max that you can get when you're retraining everything from scratch in the cumulative scenario is still far above the replay. These are the replay rehearsal baselines that sort of like combine the data from the past with the current batch. So as you see, they are sort of going towards the same direction, but still the baseline, which is the cumulative approach, is further above. Perhaps with some more constraints or assumptions that you mentioned, this gap is going to be smaller, but overall it exists. So there is still a gap between the replay, so rehearsal methods, and the cumulative baseline, which assumes that you have access to the entire thing, at least from empirical point of view. The other thing that replay methods suffer from or are limited somehow is that the accuracy improvements with respect to the memory size, so with the memory growing as a buffer of data, are diminishing. So you can expand your memory with the samples from the past, but unless you keep all the data, you will see that this improvement in accuracy will start to diminish. So we would sort of, see this logarithmic diminishing return. Also, the size of the buffer at some point, when you have a buffer that is so big that you need to store the entire data set, it becomes really problematic with respect to the size of your model and with respect to what you actually want to keep in memory. So for ImageNet, for instance, if you want to just keep 50 images per class, and ImageNet is a fairly complex data set with multiple classes, you would need to have 7 gigabytes of memory just for the storage of samples. It's pretty heavy, huh? It's not something that you would go for without thinking carefully about your limitations. And also, if you think about replaying the data from the past, these are the samples that were already observed by the model. So we would have a lot of redundant forward and backward propagations within your network, which also ends up being computationally inefficient. So in general, replay, like a full replay, is not problem-free. There are limitations, and there are reasons why people looked into this group of methods, looked into this type of strategies solving continual learning, and that's why we have replay methods as a group. It looks like we're sort of doing 3D. Oh, now it's better with the split of channels, but let's assume that we have it right now. So the first method for looking at the replay and maybe tweaking it a little bit so that it works better is how do we, is the answer to the question, how do we pick the samples for our buffer? How do we use some fancy or less fancy heuristics to pick the samples that we will store in our memory buffer? The first obvious approach is just by random sampling of your data and just keep adding these random samples into your buffer. This was proposed in 2019, and then if you reach the limit of your buffer, then you will just randomly replace and randomly rotate the samples in your buffer. I guess sounds pretty straightforward. It looks in pseudocode a little bit more fancy, but still it's quite straightforward to implement and quite straightforward to use. If you want to maybe play a bit more with those more complex scenarios, you can look at the buffer from multiple perspectives. You can use like ring buffer with first in, first out queue to store those samples. You can use more representative samples, for instance, those that are located around k-means. So if you, let's say, take activation functions or last layers of pre-trained base model, you map them onto your 2D space, and then you just pick samples that are the closest to the mean of those activations, you could potentially store more representative samples, like examples of your class. Then you can play with different replacement strategies. So not just by random, but maybe based on the frequency of classes in your data set, difficulty of how you classify them, and so on so far. There are different, buffer sizes per class, different sampling strategies per instance, and so on so far. Like here, I would say that you can go wild. You can pretty much try all the techniques that you can think of, and there will be some difference on the output. The bad side of this is that most of them will kind of collapse towards the same result as random sampling. So there were works on that, and it seems that random sampling is not that bad after all. Now, moving on to the methods that actually made an impact on the field. I guess one of the first methods that people sort of consider to be a milestone of continual learning is ICARL, or ICARL, incremental classifier representation learning, which is one of the first replay methods. It's a combination actually of distillation, exemplar learning, and replay. If you look exactly into the paper, there are like a couple of, in the introduction, they discussed what are exactly the continual learning requirements, which is, as a side comment, quite often the introduction for many first continual learning papers. So every single one will, begin by introducing what continual learning is, and then defining their own version of continual learning so that it fits the method that they propose. So just be aware of that. That's the beauty of, going on the railway and then building the rails as you go forward. So that's how we consider continual learning research for some time. ICARL, it consists of a couple of elements. First, the selection of the samples. So one way of selecting the samples that I mentioned in the previous slide was to use like a means of the centroids of activation vectors or representation vectors of your samples. So let's say that you have pre-trained base model and you take a look at the activation layers, and then from that you can often generate like a feature or representation of your data. Now you just put it out on a 2D space, you look how they concentrate, and you select exemplars being in the middle of your clusters. So sampling based on representation features as exemplars. This is the first element of ICARL that is relevant. The second is how do you classify? So how do you assign a label to a data sample? Here they use nearest mean of exemplars. So by looking again at the space of features, you would just assume that the closest mean gives you the label of your sample, and then you classify based on that. And the third one is the loss function. So when you compute your loss function, it's not only based on the classification error of your current sample, but you also look at the distillation error of your samples of your old samples on your new model. So remember yesterday we talked about this distillation of models. So instead of just looking at the labels that the model gives you, you also look at how the activation function at the last layer looks like, and you want to make sure that this activation do not move far away from what you learned in the past task. Here this idea is combined with buffer and replaying the data. So for the previous tasks, the distillation loss is used together with the classification loss on your current task. So these three steps are fairly well written in the paper. If you want to put it out or implement it, there's a bunch of algorithms defined in the paper. I encourage you to read it. It's very well written paper, so it should be quite straightforward. Another method which I think I would say is one of our favorite ones because it's so dumb, like even the name is kind of gives you the hint about it. And I believe that it was probably invented as a joke or some sort of like fancy, or not even fancy, like a hypothesis that people would say like this won't work at all, and then it kind of worked. It's called GDump. It's based on the greedy sampler and dump learner, and the intuition, a very simple intuition, is that you sample your data set, you put it into the memory buffer, and then you train your model only on the memory buffer. It's kind of weird that it works because it basically means that you don't need the entire data set. It's all about sampling the right data samples and then creating your model out of this. But surprisingly, it works fairly well. And I know that you are asked about, what's the size of the buffer. If it's the same as the data set size, then there's no surprise that it works. But it's much smaller. It's like the paper they give, I think, 300 or 500 samples out of the Cypher 10, I think, data set. So roughly, a couple of hundreds of samples, and then using them to train your model is sufficient for you to get a model that works not so bad. So again, maybe step by step through the method. First, you have the samples that are stored in the buffer and sampled in a greedy way so that you keep the balance between the classes as in the data set. So you don't want to have one class that is much more often stored in the buffer versus the other. There's no knowledge transfer as such. What you actually have, you can think about knowledge transfer in a sense is by keeping the buffer sort of representative of your data set. This is all the knowledge that is passed, but there's no mention or no notion of knowledge passed between the tasks. It's all kept in the buffer. Despite the fact that it's super simple, it was shown to outperform some of the early methods, including the one that I showed you on the previous slide, which was, again, on one side surprising. On the other side, it was a sign that perhaps the scenario that we are testing our models and the requirements that we put on continual learning as such is not really that well properly defined, if such a simple method works well. But conclusion for us as researchers is that if you cannot beat GDump, then better go home. It's either something wrong with your implementation or with your hypothesis or so on. Like this, you can use as a fairly simple control baseline, and it's quite straightforward to implement, easy to test. All right, so I think we also briefly touched on this when we were working out the taxonomy of our methods, but instead of a buffer, if you can use something more general than just the samples that you have in your data set, what people looked at are generative models. So instead of a buffer, what you can do is you can create or train a generative model like GAN or variational autoencoder so that you will get infinite number of samples that you can create out of noise. This was the notion that we as well looked at in our research. And then that inspired us to apply for funding with NCN and obtain the grant that allowed us to actually follow up on this path and look at generative models not only from the perspective of data replication, but also from a different viewpoint. That's where the deep generative view comes from. Our research hypothesis can be sort of worked out from this simplified discriminative versus generative model visualization. So in discriminant models, what you want to find is the split between classes represented in your feature space. What you want to find, in fact, is the the border where the classifier gives you one or first or second class. That means that when your continually learned models, your neural network or other model tries to focus on the differences between those classes. In generative model, what you actually want to do is you want to create your representation space in such a way that is general enough not to collapse within just two classes, but actually to generate much wider spectrum of data samples. So in other words, generative models, and that's our assumption, were supposed to be more robust to catastrophic forgetting because their goal is to represent the data and not just discriminate between samples. In fact, we had this, data or mode collapse problems with GANs that people were fighting against for many years. The main goal of what we try to achieve with generative models is give them the sample of data and then generate as much diversified samples as possible as a result, which in fact makes sense and gives us this background for our hypothesis. And we actually looked at this, and in the paper that we published last year, we've shown that the results, discriminative results based on the representations that we build with generative models are in fact less prone to catastrophic forgetting than those discriminative ones. And that's the leeway towards generative rehearsal methods. So methods that instead of a buffer use generative models like GANs, variation autoencoders, or the next iterations of those. The first approach that you can think of in this domain or in this group of models is that instead of using data samples, you use a learner model, which is based on the generator, so the generative model that creates the samples, and the solver, which solves a given task. During the learning, you don't use only new class samples, but also old samples generated by your generator, and you mix them together as if the old samples were coming from the memory. And at the same time, during a new task, you train a generator. So you kind of update the generator in such a way that it's able to recreate the past samples, but also create those that you have in the current batch or in the current task. So it works fairly well on the split MNIST or MNIST, the simplest data sets, and it gives you fairly comparable results to the ones that you would obtain with the memory buffer. There are several variants of this generative or deep generative replay methods that were proposed in the literature as a follow-up. The first one was to add the distillation on top of the generative replay. So you would be using this distillation loss that we discussed on the activation layers so that the samples from the past batches are not diverting too much from your expected outcomes. The additional setup was by adding the feedback. The method is called replay through feedback. And the reason why people try to add the feedback loops within this setup is because it allows you to combine the models and use the one model together with the generator. So combine the base model and the generator so that you add a feedback loop from the latent space or from the reconstruction of from your latent in your generator, and then at the same iteration you train the base model and the generator. So you don't split those training stages into two phases where you train a separate generative model and a separate base model, but you add those two together. Just by adding, like with residual connections in ResNet, you add more interactions between layers of your network. And this increases the efficiency and helps you also to regularize this method. Okay, but of course, there are limitations of generative models in continual setup, and I think that we talked about them 1 or 2 days ago. I guess you guys are also familiar with those limitations. So the main problem is that when you're modeling your generative model, or when you're training your generative model, you assume some probability, or you assume some distribution of your latent. And now, when you use, for instance, in variational autoencoder Gaussian as a probability distribution, as a distribution you're sampling from, and you include more and more samples, you start to observe that those distributions, those functions start to overlap. The result is that if you train Vi on cars and horses, the output that you are getting is not only more blurred, but it's also a mixture of those two. And it's not something that you would want to find out in your data when you're training a base model, to have a sample that doesn't look like a horse, it doesn't look like a car, it looks like some sort of creature in between. So given the encoding of the input images into a single continuous latent space, you start to observe this noise or this interference. And then it ends up with a confusion for the classifier that you're training. So that's where we are entering into the field. Last year we had a paper on solving for this overlap within latent space. We actually proposed a generative replay method that keeps the space, the latent space, well separated between the classes. And we did that with binary vectors being encoded in this latent space, and partitioning the latent space so that previous codes occupy part of the latent space. Current codes are generated as we speak, and then we keep still some space for the future codes. So it allows us to memorize samples efficiently. In fact, it can be, if you are familiar with binary autoencoders, or binary hashing in a sense, it can be the intuition is very similar to those methods. So the overview looks like this. You have a new patch of your data with, let's say, frog, horses, and so on. First step allows you to pre-calculate 3 binary codes. And we proposed the formula to do so, such that it only uses the index number of your current sample to generate a diversified set of codes. So I here is the ID, or the ordinal number of the sample that you have currently in your batch, and it gets increased with more samples that come. The output of this formula is a binary code, and then you have parameters on how long the string can be. What it guarantees is that they are well separated in the space, and then you don't need to actually store them, because the only information you need to recreate them is the current index of your data sample. So if you looked at 100 samples, the only thing you need is 100. And you go down and you create every single binary code from this. Once you have those codes, you train your autoencoder to store the information about the image within a given binary code. And then at the inference time, you can recreate those samples from your binary codes. And you can combine with your current set and train your base model like that. That leads to much better results in terms of accuracy, and also in terms of qualitative analysis. It just gives you much less inference, or much less noise in your latent space, which ends up with your reconstructions to be less smooth, less noisy, more crisp. So in the RTF, the replay through feedback, the method with feedback loops within your generative replay, you would see that once you move through the batches, so once you start to incorporate more and more data, the images will be more blurry. In the case of bin play, so our method, you would observe some artifacts after several training tasks, but the artifacts are not that obvious and that visible. And then in the comparison with memory buffer and other generative replay methods, we stand out pretty well. At least, that's what we have to do to get our paper published. So this is MNIST and Cypher10. So we were exploring more complex data sets as well, which didn't lead to much better results, but at least on those two data sets, we got it right. However, the limitations of bin play that we understood is that when you allocate this binary code space once, you cannot reallocate them. So this capacity is limited. And alignment of the codes that you already generated is impossible. Once you created them, you used your binary hashing method or binary autoencoder, they're all fixed. You cannot recompute them and realign them. This is why we thought about something a bit more complex, more fancy. And we thought about splitting this knowledge accumulation task or the continually learning the knowledge into two phases. One is encoding of the latent space and then aligning the latent space. So realigning the vectors, the features that are associated with your samples. In this realignment process, what we want to do is we want to leverage or look at the similarities between the samples in our reconstructed space. And so the overall or the general overview of the method is that with new data, you train first a local encoder-decoder architecture, and then on top of that, you have a translator or a global encoder-decoder module that combines the latent space from your current batch with the latent space you generated before. And this way you accumulate your knowledge within a data, within a latent space. So this is a bit more detailed overview of the method. You have a new task coming into the local decoder. You create the new samples and the encodings within the latent space L. You take the random samples from the previous tasks and the embeddings from those tasks, and you train a global translator that generates latent space Z. In this latent space Z, you use the similarities between the samples. You look at how similar the samples are in terms of the final reconstruction error. And then your latent space Z, in fact, is the result of the operation. You don't play anymore with the local latent space, but you store this latent space Z as the final one. There is additional controlled forgetting method for getting rid of the past data that has huge or big reconstruction errors, but I'd say that it's not as relevant as this two-step memory consolidation within latent space. And how does it look in real case? So for the generative replay, if you have task index, you would say, let's say that we have with the task number 1, you have class of ones. Let's look at the MNIST sample. And the task number 2, you would have samples with class 0. So you would see that this is the latent space that is created by generative replay method. And then in the task number 3, you would have classes 1 and 2. So 1 was already seen or was already given to the model in the first task, but 2 is a new one. So you would expect that ones should be associated somehow in this latent space with the ones that were seen by the model before, right? I mean, these are still the same classes. However, that's not the case, and you see that some of the ones are actually not aligned well with the ones from the previous tasks. In fact, they are somewhere in between those clusters. And also, you will see that the data starts to degenerate. So the reconstructions are getting more and more blurry. And in our model, in our method, the classes are well separated in the latent space. We enforce the separation of those because of a new task and new class that is coming in. And then when the class that was previously seen by the model appears, it will be associated together with the instances that model saw in the previous tasks. So this idea of using your latent as some form of memory consolidation tool is achieved. And, well, obviously this helps us to get higher or lower, depending on where you want to go, the results in the tables. And this is actually not only the accuracy of our model, but also the FID, so the generative, the threshold inception distance, which gives you the understanding of how well the generative model looks, what sort of results it's getting with the quality of the data it generates. And we are better when we extend our architecture with convolutional modules. We're even better than with the standard fully connected models. Okay, so overall, if we look at the performance comparison across different tasks, across different methods, across different tasks, you will see that the task-specific regularization replay exemplars method, on the task incremental learning, we're kind of maxing out MNIST, which is to be expected because it's a fairly simple data set. And again, as we mentioned before, if it works on MNIST in a task incremental learning scenario, probably it will work on anything. So, well, not this way. If it works on MNIST, it does not give you any conclusions. If you want to really get the conclusions, you should move to more complex data set like Cypher 10 or Cypher 100, which is actually the request that we get with our papers. For the domain incremental learning, you will see that the replay methods get the best results. And similarly for the class incremental learning. So the regularization methods are not performing well on that, at least with a split MNIST. For the Cypher 100, so a bit more complex data set, you have the EWC with rehearsal, and again the rehearsal methods, so those that are based on the memory are still higher up than regularization methods. Yeah, I think that was the main point of this slide, which gives us this conclusion that memory as such is the solution for continual learning, at least the one that we believe in. So optimal continual learning, there's a paper by Knoblauch that uses the set theory to justify why continual learning can be solved only with memory. It uses the intersection of the sets and the parameter space to justify the claim that without this overlap of, without the memory actually, the continual learning cannot be solved. And in fact, with this overlap, this problem becomes NP hard. That's the claim, and I think we had this discussion over the break yesterday or the day before on how to combine those different parameter constraints along the tasks so that we arrived at this point. And we actually followed up on that. Ooh. So we looked actually with the group at Jagiellonian University at this idea of interval training. All right. Which gets back to this optimal continual learning methods and the set overlap constraints. And in the general CL setting, as I think we discussed from the beginning, you're looking at the overlap intersection of the parameter space with previous tasks, so that you don't move from this local minima. Now, what we propose in this paper, and that's actually the ongoing ICML submission, so we still haven't published this yet, even on archive, which makes it a bit more difficult for me even to find it, was that we approximate this overlap with rectangles, and we used interval arithmetic instead of the regular scalar optimization with a neural network to find the borders of our parameter space, where we can still find the optimal solution for our tasks. So as you see, along the tasks, we kind of focus more and more on the overlaps in the parameter space, but approximate those multidimensional spaces or manifolds by rectangles. And I think I should now go back to the slides. Magic. So this was the slide. All right. So that's more or less it when it comes to the overview of the methods that we have currently available. We had talked about the regularization methods, the architectural methods, and the rehearsal with generative models or with buffer. Now what's coming up? In the current state, we are very much looking at the applications across different domains. So obviously, we've seen the images because that's the easiest for you to grasp the idea of CL. But there are also applications in NLP, audio processing, biomedicine that uses continual learning. It's not limited to a single modality, the problem that we face with continual learning. It's also not limited to just supervised learning. There are more and more works on how generative models forget, how reinforcement models can be tested or verified in continual learning scenarios. There are methods that are proposed, but most of them are using some form of toy data sets. So it's very difficult to see the results of currently available CL methods on real-life use cases, real-life data sets. There are not enough benchmarks. There is still the discussion on what the scenario or this testing scenario should look like. Therefore, there's still a lot of work to be done there. The evaluation is usually one-dimensional, so you usually get reported only on the accuracy of your method or FID or so on. There's not that much work on the combination between the complexity or computational cost of your method and the quality that you're getting. And we start to look more on the multiple axes of comparison, not only average accuracy, but also forward transfer, backward transfer, the plasticity of the network, computational efficiency. That kind of gets back to this evaluation slides that we looked at on Wednesday. It's very focused on specific simple task sequence. That's another dimension that we know that matters, like what is the sequence of the tasks that you're giving to your model. It matters. It's curriculum learning is another related field which indicates that how use, or what's the sequence of your data, of the data that you feed into the model plays an important role on the final performance. And then the question is, what happens when the model saturates? Like when you have you maxed out all the metrics, do you like selectively forget past knowledge? How does this selection works? In living organisms, if you don't use certain part of your knowledge for like extended period of time, you would start forgetting it. Like, if somebody learned French or German in the preliminary school, but then never used it, it would naturally be kind of forgotten. So how do we model those scenarios in CL? So the direction of research goes towards real stream or real data streaming and feeding that to the model, increasing the modality, so not only looking at the single modality, but also more. The evaluation in terms of knowledge transfer more than just catastrophic forgetting. So catastrophic forgetting is a spectacular phenomenon that people were excited about. Now, it's not only the forgetting that we look at, it's also how we transfer the knowledge across the tasks. And then the ability to organize the memory, like the latent space optimization or the alignment within the latent space. These are the direction that we're moving forward. If you're looking for additional materials, there is a bunch of links on GitHub and also a bunch of papers. Obviously, the best source is current editions of top machine learning or computer vision conferences like CVPR, ICML, or NeurIPS. But here are, I'd say, like not exhaustive, but representative list of libraries that you can try. Avalanche is supposed to be a general continual learning framework that Vincenzo is promoting, the guy that I used as an inspiration for those slides. But there are many more, and then Avalanche is probably not. Do you actually use Avalanche for the exercises? No.
Yes.
You use.
This
okay.
is the library that will probably crash if you use it.
Yeah. So again, the beauty of new field of research, you will see a lot of bugs coming up. There are a bunch of survey papers that I encourage you to read, although they are updated again like every couple of months. There are like papers on the theoretical aspects of CL as well as those on the benchmark scenarios. And actually the organization that you want, if you were interested in the field that you want to follow, and also the Slack group and so on, is the Continual AI. It's a non-profit organization and it has its meetups, its community. And now we have Koala, which is the conference organized by folks from DeepMind and I think some other, that will be the first edition this year. You can look it up as well if you're interested. It's going to be probably the test edition this year, and that gives us like a slight leeway towards the promotion of the events that we're as a group are involved into. And there will be two. First is the machine learning summer school meets neuroscience. That's going to be in Krakow this year. The registration is already open. You can submit your extended abstract. It's funded by NAVA, so it has a very strong international character. There's going to be a bunch of speakers coming up from DeepMind, Google Brain, Oxford, Research, Microsoft Research, and so on. So if you are interested in, well, not only continual learning, but in general the neuroscientific inspirations getting into machine learning, this would be a fairly interesting event for you. I think the registration closes within 2 weeks, if I remember correctly, so get your extended abstract ready. And then there is ICML workshop that we organize in Baltimore this year. The name is the Dynamic Neural Networks, and we discussed abbreviation of that yesterday, which ended up with DEAN. I'm not sure if it's going to fly, but the hardest problems in computer science are naming. Once you have the naming, then everything goes much easier. But there will be a few speakers from like Tina to Francesco Locatello from Amazon, and a few folks from Furan and Tsinghua. And the topics are also related to continual learning. So there's, in general, dynamic routing, early exit methods, conditional computations, as well as applications of dynamic networks and continual learning. So if you're working in the field and you want to, try your luck with top conference and workshops at it, that's a good place. Okay, and obviously that's not only my work that I'm presenting, it's a lot of collaboration going on both with Tuplux and Warsaw University of Technology and Jagiellonian University of Technology, supported by huge names and funding agencies, so you usually have to mention them as well. And well, if you're still interested after those 3 days in CL, you're happy to explore this topic more. We are open for PhD candidates. We have in CV Lab now 16 people with 4 faculty, 4 postdocs, 10 PhD students. We have already 10 A-star conference papers on our record and 3 ongoing research grants. And 0 animals were hurt during all the experiments. So, although we have a cat that we try to sort of fit in within our logo, but the cat was not hurt. Okay, so I think in summary for today, we looked at the replay methods, both using memory buffer generative models. So you should be able to move quite nicely throughout all those methods that were proposed so far. Replay is effective, but it has some limitations regarding the memory buffer that you should be aware. Now, if you want to switch a memory buffer to a generative model, then you're free to do so, but you have to be careful about latent space and how you model your latent space so that you avoid overlaps. And yeah, just try to explore a little bit more of that within today's session and within the assignment. So the assignment is due by the end of the month, and it's going to be based on the exercise sessions that you had, and you will have in 15 minutes. And feel free to ask any questions. I know that today it was not too many question pauses, so if you have any questions, feel free to ask them now. And thank you for attending. Any questions?
I could technical one. So I downloaded the slides and I had a problem with copying or searching in the slides, like text or searching text.
Okay.
But, I'm not sure if it's just a problem or if it's related to the slides.
Okay.
It's possible to check if it works and about the version of slides which works.
Okay, I'll try to download it myself and do the. I'm opening with preview. What are you using? The
Probably Chrome, like just Chrome.
Okay.
Like when you copy the text, it's kind of gibberish.
Okay.
So like if it would, and because of that, we also can search.
I use the downloaded version of this one, but
I
if
noticed that I checked, I created one slide myself and downloaded them, and it worked for me. So I'm not sure why.
maybe another good idea would be just to share the link to the Google Slides. That probably would help, right?
Yeah.
So I can maybe send you the Google Slide link so that you. Is that okay, Philippe? Sure.
Thank you.
I have a question. Do you know whether these continual learning methods are, for example, used in or any applications in biology? For example, know that there is like a huge problem when you work on a single cell domain where like each new lab and each new patient is actually like the problem on its own because like, there are many so-called batch effects.
Mm-hmm.
So the new lab, these results should be somehow the same, but they are still different. And first, like whether you know whether these techniques are applied in this domain.
So application. The question is about the applications of CL in medical domain.
I think that for me this is like the best candidate. So I'm curious whether maybe you heard about this particular application.
So here I would refer you to Wojtek, actually, who's working with Krzysiek Geras at the NYU in medical domain. Not sure, Wojtek, do you have any, like, we look at this mostly in like medical imaging domain, right? Not that much about general medical applications. Have you heard about any papers in like general medical field?
Not about biological.
Not about biology. So usually what people do is they think about this medical imaging perspective that I mentioned before, which is like lack of access to all data from previous patients. This is quite straightforward and the use case is obvious. With biology, we should probably look, or we should start, as Eva mentioned, collaboration ourselves and try to be first or leaders in the field. Any other questions? Yeah?
Do you know if anyone has tried to use mix-up to store the images from previous tasks? Because it seems to be quite intuitive to use, because mix-up uses a linear combination of images and then train model on linear combination of labels.
Mm-hmm.
And then it seems to be a straightforward approach. Because you mentioned that the problem was storing, for example, the 50 images per task per movement.
Mm-hmm.
But I guess mix-up can be applied in other scenarios where we can just take a linear combination of a few images and use them as a reminder for our model.
So mix-up is like a compression algorithm, or?
It's data combination technique where we just train, where we take linear combination of images per pixel and linear combination of labels.
Okay, so but the point would be to reduce the size of the data that you store.
Yes, using this linear combination as a reminder.
Mm-hmm. I think that there are methods that are focused on reducing the size of the data samples, or as I mentioned with these buffer methods, to sample them better. The focus, and I guess it's a good idea to check whether this one would work as well in this setup. I think the general goal of CL is not that much on the compressing the data as it is on accumulating the knowledge with the assumption that you have infinite number of samples in the long run. So even if you have the best compression algorithm in the world, or the best reduction of the number of samples, number of bits per sample, you would still run into the problem of accumulating this knowledge and not forgetting the one that you already acquired. I think the accent or the problem lies not necessarily, although it's verified by evaluation, the computational complexity. It is not the main purpose of CL methods to reduce that.
But isn't CL isn't it a bit artificial problem, because humans also tend to forget, for example, how bad looks if they don't see that for 20 years.
This is a very good question, and I'm happy that it only was asked at the end of the course. Otherwise, you would be confused why we are here. It is ongoing debate whether we actually have a real case for continual learning as such, or it's just an umbrella of problems that we put together, and because of the overlap of those requirements, it's not, in fact, met in reality. So, there are different approaches to answer that. Like the easiest would be like it depends, because it always depends. Like we want to, in a sense, the inspiration comes from living organisms. So yeah, we have some forgetting. Yeah, we have some knowledge accumulation, but we don't assume that the moment that you start learning a new skill as a human, you instantly forget everything that was in the past. And this, I think it's kind of a blurry line, whether you say that, okay, it's fine if you forget something that you haven't used for like 5 years or 10 years or 100 years, but then there is your PhD defense exam, and people would ask you like, what is the complexity of computational complexity of sorting or bubble sort. And you're like, but I did that when I was at my bachelor and now I don't remember. And people will be like, yeah, well, but you're a PhD in computer science. You should always remember that. I guess it's a philosophical discussion whether you're allowed to forget at some point the previous data or previous knowledge or not. My answer to that would be we are so far away from the point where we have even a model that is able to acquire several tasks that are similar that we're not ready to answer the question of whether this would be possible to solve in the long run, this entire set of continual learning requirements. It may look a little bit artificial. I think right now we're just baby level in terms of solving the base problems. When we get to this more complex tasks, we'll probably ask this question again, and then maybe the answer will be different. Okay, I think that's. Oh, go ahead.
You mentioned the unsupervised learning,
Mm-hmm.
and maybe you could pose some nice literature about this year in unsupervised learning. Yeah, you could just put those slides.
Yeah, I'll look it up. I think I had 1 or 2 papers on that and the related work of one of the papers, but I'll put it on the reference section on the slides, and I will share the link so that you can maybe go through this as well. Does that work? If that's it, then thank you so much for attending, and good luck with the assignment and the exercise session.